Let's welcome Nao again for the second part of this lecture.
Okay, thank you for coming back. So I'm gonna continue some discussion on ramping and also then the next topic. And both of these parts are related to what we call states. So in states, in reinforcement learning, I briefly introduced that in the previous examples that corresponds to what location the agent now occupies and things like that. And oftentimes the state is so key, but we don't really deeply think about it. So that's actually a very important issue, and I'm gonna present some examples in that. So going back to dopamine ramp, so I presented some evidence showing that ramp is actually changing value, and assuming that more convex value function than exponential, then you can explain positively ramping dopamine signals. We did some experiments to tease apart what is causing ramps, and one of them is this one. So many experiments that show the ramping dopamine signals are done in navigational context of freely moving animals getting closer to the world. So first, we wanted to understand whether ramping signals requires this kind of spatial components. So to do that, we just had some. The bar is going to move from the top to bottom on the computer screen. So the actual stimulus is like this, so going down, and then when this reaches at some point, then give reward. So we got rid of all the spatial component or navigational component, and we just choose how close they are to the reward timing. And this was sufficient to cause ramping dopamine signals, indeed. And also we did a teleportation and speed migration in this condition. And we can see this transient response evoked by just quickly moving bar from one location to the other, and also quickly moving, changing the speed, we can really change the magnitude of ramp. So navigational context, so even animal moving to go is not required, right? Just a cue that tells the animal that you're getting gradually closer and closer to the reward, either in space or time, that is sufficient to cause ramping. So this is very similar to the experiment that I presented. Now, another experiment. So we have done a lot of experiments with classical conditioning paradigms, presenting cue and followed by reward. In these conditions, we typically did not see ramping signals. And this is also demonstrated in this experiment, where olfactory cue was presented and reward came after some delay. In this case, activity actually ramps down. That's also a common feature that we observe. The same neurons recorded in virtual reality, it shows ramping up. So the same neurons can ramp up or down depending on the task. So we thought hard about what is causing the difference between these conditions. And one idea, so I don't think we completely understand it, but I'm going to present a model that tries to explain this. Yes?
In the bar experiment, what is the
So the sensory information telling that the reward is gradually getting closer and closer.
But there's no feedback there.
What do you mean by feedback?
It's kind of passive, no? It's kind of a passive experiment.
Yeah, it is passive experiment.
And now you're saying that in the passive case there is no ramping, so that's why I'm asking.
So
it's a bit like
so this is not passive or not. So so this is the difference we think is whether the stimulus continually give the information about the proximity to reward. Whereas in this case, just the blank time, elapsed time, is used. Any questions? Yeah.
Sorry, I didn't get the condition when it goes down.
Yeah. So this is the video. Bar goes down, and when bar comes here, then animal gets reward. Yeah. So bar is here, then animal knows that reward is not going to come now, but after some time. And then this duration gets smaller and smaller as the bar gets closer to the location here. Yeah. So the point is, the cue is continuously telling the animal how close you are to the reward. And in typical classical conditioning paradigm, it's not done. So you give the cue, and then after 3 seconds or 2 seconds, you have to wait. But where in this space is not given. Yeah. So we think that there is a difference. Yeah.
So there is a rocking activity, and then there is a peak at the time of the reward.
So,
but
yeah.
But that reward is predictable, totally predictable, no? Or why?
Yeah, they really know. Yeah, there may be still some uncertainty there, and also this is big, but also this signal doesn't quickly decay, so it's kind of added on top of this signal. Yeah. But yeah,
there is no reward. There is a negative.
Yeah, but again, because of the slowness, it might not go like this, but it goes like that. Yes. Okay, so here's the theory. So we think that state uncertainty might play a role, and what I mean by that is in the classical conditioning paradigm, when there's no continuous feedback, uncertainty about where you are in the state will increase because the uncertainty about timing increases with the interval time, right? So so just pay attention to red. Okay, so the uncertainty about time could be relatively narrow, but as the time elapses, this gets lower and lower, more uncertain. And one time step further, you have more broad distribution. Now, when you're getting feedback about where you are in the state, then this gets corrected. So you have relatively constant uncertainty about where you are for the current location, and also the next time step, right? So there's fundamentally different state uncertainty structure between these two tasks. Now, what's interesting about this is when there's uncertainty, like this kernel, then there's convex value function. If you have convex value function averaged or convolved by this kernel, what is your value prediction? Value prediction is going to be here or overestimated or downestimated. Yeah? Overestimated. Why? Yeah, so you have more increasing positive part. So if you draw this curve with this kind of kernel, you end up overestimating the value, right? Is this okay? Yeah. I mean, that's kind of the definition of convexity. But if you have wider width, then you get more overestimation. Okay? Now, if you have that, and now you're computing TD error, so comparing value between two time points, and the future state is going to be more uncertain. So you get more wider kernel. So what this result makes is the value estimate is more overestimated for the future time point compared to current. Yeah?
The value is just to be monotonically rising, right? It doesn't need to be convex to get this result.
I think that convexity is important to overestimate. If it's linear, you don't overestimate. Yeah.
Sorry, I don't understand the argument being made. Can you say again?
Yeah.
Why is it overestimate?
Yeah, so if you have a wider kernel, right? So in this case here, red, compared to pink, you have more wider. So basically, you're getting more steeper increase here, more and more if you have wider width.
The tail includes more of the steep part?
Yeah.
But I don't get it because it's symmetric here, right? Like it also includes more of the small part as well, that's what I understand.
Yeah, because this is shallow, and then getting steeper on the right.
Increasing this.
Yeah, because of the convexity.
Yeah.
Right? So, okay. In an extreme case, if there's no uncertainty, you just end up going no overestimation. So first of all, just by this, you get something like more convex curve locally compared to the true value function. Okay, but this itself doesn't create ramping dopamine because I should explain another thing. So now you move one time step more, like here, and then you have the same problem overestimating like this. But what is critical is now the value of this location is overestimated for this more so than this in this case. Meaning that if you are computing TD error, right, value could be positive term or negative term. And this means that when value is used for positive term, it overestimates more than when it is a negative term. Right? So overall, if you're using this kind of overestimated TD error, you end up overestimating TD error. That means that the value that the animal learns is going to be overestimated. Is this clear? So what ends up occurring is that if this blue is the true value function, using TD error subject to this state uncertainty is going to end up having overestimated value. Okay, but if the system reaches to this value function, a black value function, then TD error actually becomes 0. So there's a convergence point even in this case, as you would expect. If you're running this TD learning mechanism, it converges to some point. But because of the inflated prediction error, you are converging at the overestimated value. So one funny assumption that we make is under the assumption of normative system, right? There may be some correction system that reduces TD error so that the system, if it goes back to the system is able to converge to true value function. So correction term has to be quantitatively defined and precise, but there may be some direction, some correction that is consistent with this direction. But now, once you do that correction, you end up having this kind of locally convex value function effectively. And therefore, you end up having a positive and ramping TD error. Okay, so it's a little bit convoluted argument perhaps, but this summarizes the logic, right? So the state uncertainty causes overestimation value because of convex value function, and greater uncertainty in the future states compared to current state, and this makes the value function more convex locally. And sensory feedback causes inflation of RP, and a normative agent. I should explain this part better. So the reason this goes down is because the sensory feedback is coming. So the red curve here becomes narrower than the purple one, right? So this is the role of dynamic sensory feedback, telling where you are in the state, right? So because of that, sensory feedback causes inflation of RPE, and a normative agent would correct that to prevent it from overestimating RP and value. And if once you try to correct it, then you end up having remaining this more convex value function. Yeah. So I don't think this is the final theory, but by assuming this, we can explain that. But I guess you might not be convinced, right? So we wanted to do some experiments to at least test some component of that. Yeah.
So why this explain? Why without the timing case there is?
Yeah. So the timing case, it turns out that you can actually converge to true value function because there's no inflation. So the value function for the next times after transition, this state values remains here. So there's no overestimation of RPE. So it converges to the true value function. So it's not necessarily state uncertainty per se, but state uncertainty being corrected by sensory feedback that causes the dopamine signals ramp. Okay, so we wanted to manipulate state uncertainty. That's what you do, right? So in this experiment, we gradually darkened the virtual reality feedback. Okay, what would you predict? So you're now increasing the state uncertainty. What do you expect? What's your prediction? Less ramping. More ramping. Who thinks more ramping? Who thinks less ramping? Who thinks both? Who thinks both? Okay, so this is a standard condition, right? And then if you increase state uncertainty, that's the primary reason to make the value function more convex. So you would get actually greater ramping at the beginning. But then what happens is, if you just make the scene completely dark, it becomes the same as the purely timing-based condition, right? So at the beginning, because the state uncertainty is the reason for ramping, it increases the ramp. But also, if it gets completely dark, you get ramping down. So we actually create not ramp, but bump. So we end up creating bump in this experiment. So this is a theory prediction, but that's what we actually get in the experiment. So remarkably, this pattern is what we actually observe in the experiment. So at least we are confident to say that state uncertainty seems to be playing a major role, in a way consistent with our model. But this model might not be the only model. So if you come up with better model, I'm happy to listen. Yeah. Did you get the experiment? Yeah?
I just want to make sure I understand the prior slide, the series. So, can you go back one slide? Or
Yes.
Okay, so the last bullet point, basically, I want to make sure I understand that point. So, because you have overestimation, you need to make the exponential rise sharper, right? So, it's a higher exponent to compensate for that. Is that the idea?
So can you say?
I'm trying to understand the final point at this point. So you have overestimation. Because of that, you have, I'm not trying to have the signs right, basically. So the result then is that you need to have a steeper exponent to compensate for this. Is that right?
That's right.
Okay.
But it is because after correction, you end up having the effect of state uncertainty increasing for the future. Yeah. Okay.
So what do you targeting?
Why do you darken the cube? Why not just some trial showing dark the cube and some trial showing normal cube? Then in the trial with low contrast, then you will have like less ramping. then can compare across between trials.
That might happen, yeah. But I think this is even non-trivial. So at the beginning you increase and then decrease. That's not really
more complicated.
trivial. So we thought that this is a good test, but there may be other ways to test. Yeah.
I'm a bit confused about the sign.
Yeah.
Because if you expect more and more sense, if you less,
Yeah.
in some sense you're disappointed, dopamine should go down.
I see. Let's see. So the notion is there's some true value function given the structure of the task, and then we're thinking about how so the system will converge close to that, but then how this will deviate based on these uncertainties, right? So we're thinking after some learning and then get close to the true value function, what will happen? So at that point, it's really...
Is this correction step crucial? Because here it seems you are disappointed with that, but maybe you correct for that, and then, I mean, that was your last sentence in your part.
So, yeah, well, I think there's always kind of equilibrium where if the expectation is too high, then you get negative prediction error, and then this will go down. So this is always happening with some stochasticity in the system. But also, on top of that, on average, what might be happening is this kind of dynamics. So, okay, so I don't think this is the final theory, but we have some theory, and then test at least supported some aspects of that theory. But I think this needs to be explored more. But I think this example highlights the importance of thinking about states in reinforcement learning, right? So it's not just complete serial compound, just stimulus and then ballistic state representation that is activated by stimulus. It's much more nuanced and complex, and we have to think about states to really understand these kinds of models. Okay, so and I just want to make a short comment about this new study. So how many of you actually know about this study? So this study was very sensational in the sense that it's published in Science, and then this study really tried to trash TD learning and then propose a new model. I don't have it, well, maybe I should briefly mention that. So this model is called a retrospective causal learning model, and when something important happens, the model looks back and then try to look for the causal stimulus that is important in causing the important event. And it uses different mechanisms than TD. And this was highlighted even in economics. So this is a journal for economists, and even beyond neuroscience, it had impact. Okay, so my postdoc has a father in economy, and then his father really was concerned that the model that we are working on is now end. But anyway, but the simple point that I would like to make is that so I showed that dopamine signals have this derivative-like property. That was the theme of the first part of my talk. And ANCA actually does not have that property. So in the supplementary figure, they actually presented something like this to claim that they had derivative-like property. But if you actually look at the trace, it's like this. There's no transient response. And then they just plotted it differently than originally studied to mislead the audience. So there's no mechanisms for derivative-like computation. And we think that detecting changing value is really the central property of dopamine signals, and this model does not have that. So that's one problem in this model, I guess. But I think this model has very interesting aspects, so we are still exploring, and there are other issues to be discussed, but this is my very short comment based on my first part of my talk. So, these studies are done by Him-gu, and I should mention that a lot of theoretical part came from Sam Gershman, my collaborator at Harvard, and also his student John Michael. So John is the person who developed this state uncertainty-based model to explain dopamine ramp. Okay, so that's the end of my first part. Yeah.
Excuse me, I just want to clarify. So you mean the data doesn't support a claim for the perspective?
Yeah.
So that was the
So this is purely modeling result, right? And then their model, modeling the teleportation experiments, did not have transient response, despite the fact that we saw this in the data.
which means, could you just elaborate a little bit more? Which means this data is not accurate, or?
So the data does not match with Anka. I think what we want to understand is what's happening in the data, right? So the model is not appropriate to explain the data.
I see.
Yeah.
Thank you.
Okay, so let me move on to the second part. So the reinforcement learning and dopamine, and continuing discussion on states. So we have this TD learning model that explains dopamine response, and also we have a little bit more mechanistic model, but I think this has very simplistic state representation. So stimulus triggers the sequence of activation, and using that, value is computed by weighted sum of these activities. And I think in this Schutz, Diane, and Montague paper, they explicitly discuss that this complete serial compound should be defined for each stimulus. So in the presence of many different stimuli, having this delayed tap line or complete serial compound could be unrealistic, right? So how can we understand that? And also, let me skip that because I mentioned that. But so there's some interesting experiment that demonstrated clearly that this simplistic TD learning model is not the only way that the dopamine signal is computed. So this one, done by Bromberg Martin in Uchida Osaka's lab, was doing reversal learning task. The monkey fixates on the fixation point, and then saccade to the left or right. And in one location, they get reward, and the other not. So they then eventually reversed this relationship. And then what happens is, in trial one, so previously rewarded one activated a dopamine response when this cue appeared. So this is a cue evoked response, okay? Was high, previously rewarded one, and then previously unrewarded one caused some dip. So that's natural. But when reversal happened, and then experiencing one reward or one omission, then the response flipped. So in this case, you're seeing almost complete flipping. So previously unrewarded one, just by having one experience of reward, our response flipped. Okay. And then previously rewarded one, now unrewarded, and just one experience of unrewarded trial, the response shifted. Yeah, so that just shows that the learning happens very quickly in one trial. Okay, but what's interesting is when the monkey actually, let's say, did not receive reward, okay, but then sorry, I should say, previously no rewarded one, so the response was like this. And then in the next trial, after reversal, the monkey did not receive reward for blue target. Okay. So despite the fact that the monkey did not receive for the now rewarded target, the response was slightly increased. So without experiencing reward directly, the representation about this Q target was updated. Right? So as if they are understanding the anti-correlation between the two targets. So with the knowledge that these two targets are uncorrelated, anti-correlated, then experiencing one, you can update the other one without even experiencing that. This is what's happening. And you can prove that with dopamine response. So this cannot be explained by simple TD learning model with complete serial compound. So this is one classic example showing that model-based or some inference-based process must be coming in to influence dopamine response. But you can still put this in such that the value is what is computed based on different mechanisms. But then after that, the system computes the error. So that it just points out that the value could be computed in different ways, not just model-free, but model-based, and so on and so forth. I think the evidence also comes from human experience, such as what Natalia did. Now, so I will talk about some experience that we did, which is, this is done by my student Clara Starkweather, and this is a very simple task. So the order queue comes on, and then reward comes. In this case, we had some jittering in the time of reward. So there's some uncertainty about when exactly reward is going to come. This is Gaussian, discrete Gaussian distribution. And now we have two versions of the task. The only difference is in task 2, reward is omitted in 10% of trials. Otherwise, the two tasks are the same. Okay? And we measure dopamine response by monitoring single dopamine activity with optotagging method. Now, in task 1, when reward probability is 100%, the response to reward was gradually decreased. So when reward came early, big response. When reward came late, smaller response. Okay. Now, if you just add 10% reward omission, this tendency flipped. Okay. So just adding 10% omission really changes the way that dopamine neuron respond. And the simple explanation for, phenomenological interpretation is, so because this represents prediction error, the more surprising reward will create bigger response. That means that expectation, so the reward is less and less surprising across time in task 1. But in task 2, reward is more and more surprising as the time elapses. Yeah? So this kind of dynamic change in expectation is not something that is in the TD learning system, TD learning model, of the very classic one. So if you just use very classic TD learning models, it doesn't distinguish these two conditions. So something more is going on. And so the way to think about this is intuitively, imagine that you're in Japan, okay, and then you're waiting for a train, and then this says that the train is going to come at 2 p.m. And then the time elapses, and then you're getting closer and closer to the 2 p.m. Your expectation about train is going to come will increase, right? So the train coming at the given moment is less and less surprising. Things like task 1. But if you are waiting for a train in the United States, Amtrak, right? Or I don't know if you know that, but I also experienced that as the time elapses and then train doesn't come, you start thinking that maybe train might not gonna come at all, right? Yeah, so depending on the context, your expected structure of expectation is going to be different. And this is to do with some Bayesian inference. Given the evidence that the train has not come yet, your expectation about train coming is going to be updated. Yeah. So, inspired by Nathaniel's model of hidden Markov model, or partially observable hidden Markov model, we applied this framework to understand it. So in task 1, as soon as the order comes, you're sure that you are in, sorry, I should explain. ITI is inter-trial interval, and ISI is inter-stimulus interval. So when stimulus comes, you enter to ISI, and now waiting for reward, and reward is going to come 100%. And as soon as the reward comes, you transition to ITI. So these deterministic transitions happen induced by stimulus or reward. Okay, so this is in task 1. So your belief about the being in ISI is 100% as soon as the Q was presented and remains 100%. Now, in task 2, when the stimulus is presented, your expectation about being in ISI increases to 90% because that's the total reward probability. But as the time elapses, and then you have not yet received the reward, the likelihood of being in ISI actually gradually decreases with Bayesian inference. So now the likelihood of being ITI or omission increases over time. So if we incorporate these states into the simple TD learning model, so instead of having this complete serial compound, we have this belief state representing probability of being ISI versus probability of being ITI. Now, if we plug in this kind of states and some other modifications, now we can reproduce these increasing or decreasing dopamine responses. So, yeah, so this experiment shows that the considering more state representation that is reflecting the actual inference process that happens in a given task might be sometimes important to explain dopamine response. So many people argue that the failure of very simplistic TD learning models really jump on to conclude that these dopamine responses cannot be explained by TD, so we have to look for something else. But sometimes we can come up with this kind of state representations to explain what's actually going on under the framework of TD learning. Okay. So that's one study that we did several years ago. And then I would like to talk about a relatively new study that's in bioRxiv, done by Selina Chan, in collaboration with Sam Gershman and Jay Hennig, his student, his postdoc, and also Matt Burrell, he's my postdoc. So the reason I talk about this is also related to this anchor, so the new model that was proposed in science paper. They claim that the experiments, based on the kinds of experiments that I described, they attack the dopamine TD idea. Okay, so what is contingency? Contingency is a very interesting idea, also related to one of the credit assignment issues that we discussed earlier, different ways of thinking about credit assignment. But in any case, so let's imagine that stimulus A is presented, and then reward comes at some point. In this case, reward is always preceded by A, so there's some certain relationship or contingency. Now, in the second condition, the reward is preceded by A or nothing. So in this case, A does not actually predict or increase the prediction of the reward, right? And in more extreme case, the bottom one, as soon as the A is presented, reward is unlikely, very unlikely to come. So, in this case, so in these conditions, the A tends to predict precede the reward. This is a positive contingency. And more formally, this could be defined by a probability of reward given the stimulus A minus probability of reward given there was no stimulus, assuming that these trial structures. And this is the contingency. So what's interesting is in the second condition, you have exactly the same number of reward preceded by A, but only in the top condition, the strong conditioned response happens. In the second case, the conditioned responding, or in this case salivation, does not happen. And even in this negative contingency case, you could have decrease in salivation compared to the baseline. So it's not just the contiguity.
I want to see the blue wall versus the negative wall.
No reward.
Yeah,
The blue one.
Yeah, so this one is preceded by A, yeah, maybe I miscolor.
Yeah, yeah.
So, but this one negative, this one is negative. Or no Q. So in total, this is negative.
So the blue one is like a shock. So the blue one is like a shock. It's a negative reward.
Yeah, it's not completely negative, but in total, it's negative. Yeah.
I think he's confused. I think the blue rewards are also rewards, you just colored them blue.
Yeah, that's
They're the
right.
same.
They're not a different type of outcome.
It's time sequence. It's not following the A. That was what we say. So basically, it's the second part of the equation. That's what we mean by negative contingency.
Yeah.
So the reward is preceding the QA, but not following the QA.
Yeah, so I didn't explain quickly, but this red is presented right within the stimulus A.
Yeah.
And then blue is when A is not present. Yeah. So this definition has some issue because you have to define trials, and then that is something that we have to fix at some point. Yeah, but the point, I hope you get the point, right? So just by having this red Q reward does not guarantee that reward is associated with A. You really have to think that at the baseline, what is the probability, and then how much Q increase or decrease compared to the baseline. That is the contingency, and that's the determinant of how efficient the learning is going to be. Yeah? So this is a very classic concept, even proposed by Rescola, Wagner's Rescola. But we did not know how dopamine neurons change their activity based on contingency, so we started this experiment even before this science paper was published. But the science paper really used this paradigm, so we had some discussion about that. Okay, so what we did was to develop some paradigm in mice and using classical conditioning paradigm because of the controllability of stimuli and reward compared to operant version of it. So similar to I presented in the previous example, during conditioning, we have positive contingency-based training conditioning. So A predicted reward with certain probability, in this case 0.75, and B predicted reward with zero probability, and there was background trials. So there was no Q in these background trials. Now, during degradation, we add reward with this probability 0.75 during the background trials. Okay, so the A followed by reward, so that part is not changed. We just added this background reward, okay, in the trial intervals or blank trials. Okay, so if we do that, so now we can calculate contingency, right? So the probability of reward given the Q versus the probability of reward without reward. In this case, during conditioning, this is 0.75. In the case of degradation, the probability of this part has not changed, but we got this this part. So depending on the trial B or trial C, no reward trials, we can just add based on the probability of each trial type. Right? So you get 0.25. So overall contingency is decreased. Now, this is a measure of association. In this case, we are using anticipatory leaking. So leaking of the water spout before receiving reward. And during conditioning, this goes up and then get to a steady state during these 6 to 10 sessions. Now, after degradation, the conditional response, this anticipatory leaking decreases. So we managed to have this contingency degradation paradigm in heterotic mouse with olfactory Q. Now, one thing that is interesting is after degradation, there was some baseline leaking that increased. So that's one measure that we can obtain from this paradigm. Now, you might be wondering that in the second degradation condition, you're getting more reward, right? So maybe animals got satiated and less thirsty, and therefore they might have stopped leaking. So we have a third condition, which is the reward was given as in the same manner with degradation, but preceded by a new stimulus, order C. Okay, so that's the only difference. The number of reward given was matched, but the new reward in the cued reward condition was preceded by a stimulus. And what happens to the behavior? Can you predict? It turns out that degradation doesn't happen. So the leaking stays high, and this disputes the idea that this is due to decrease is due to satiety. So we get this kind of V-shaped curve, conditioning, degradation, and cued reward. And if you think about contingency here, the same calculation if you do, the contingency for order A is actually like this. Between degradation and cued reward condition, the degree to which A predict increase of probability of reward remains the same here. So this actually shows that the behavior dissociates from a contingency as defined by this classic definition. And this was one of the points in the animal psychology literature that contingency is not a good measure of the behavior of conditioning. But I will come back to this. Now, then we measure the,
So Paris, in the top panel there, are you regarding the green and purple as the same and just noise due to the statistics, or do you think there is some small effect of the satiation or some other effect that's driving like a real difference between the conditioned and the cued reward?
Yeah, I guess the difference is not statistically significant, but also the main point would be big difference between degradation and cued reward. Okay, so then we measure dopamine signals in the nuclear skin box. Now we are using multi-fiber optometry, so we can measure several points at the same time, or up to 10 or 20. Now, but I'm just focusing on the ventral side and general response pattern. Okay, So during conditioning, reward response goes down, and then dopamine Q response goes up. So that's the typical response. Although the decrease is not big, partly because we are using relatively low probability of reward, 0.75. But in any case, the main point is during degradation, Q evoked dopamine response goes down. Okay. And what's interesting is that Q reward condition, this decrease did not happen. So mirroring the behavioral change that I described earlier. So just plot the dopamine signals in a similar way, you get this V-shaped curve. So this response is sensitive to the presence of QC. In this case, the response does not decrease. And this is similar to the anticipative leaking pattern. Now,
Can I ask a question? So if I understand correctly, so in your degradation condition, you basically suggest that A is not a necessary condition for reward. Because when reward happens, sometimes it follows A, but sometimes it does not.
yeah.
And so I'm wondering if you change it to be a necessary condition, but necessary but not sufficient condition for reward. That is, whenever reward happens, it always follows an AQ. But just sometimes when A happens, there's no reward afterward, and the result will go back to the formal tree. So the key point is it's not necessary, right?
That's actually the thinking very close to the anchor model. So you get reward and think what is preceding given reward. And in this case, 100% A.
I think that was their original argument.
Yeah, that's their original argument, right? So in this case, the reward is preceded by A or no Q.
Yeah, so it's
So this goes down to half that. That's how anchor model try to explain. But that doesn't work for this one. Yeah?
I see. So in this situation, A is still necessary.
So
It's not.
what anchor predict is reward is preceded by either A or C.
Yeah.
So the same, similarly to this one, the contingent, the relationship should decrease. Causal relationship decrease, but it doesn't decrease, right? So this Q reward condition, we did that for the sake of controlling for society. Turned out to be very important for distinguishing these models. Yeah. So did everyone get that? So if you have not read the anchor model, the key point is, as I said, anchor model tries to look back what happened, what preceded an important event. In this case, reward is preceded by A or nothing, or A or C. In either case, relationship between A and reward is degraded in this case, and this case. Yeah? But in the data, both behavior and dopamine response, the decrease did not happen when the reward was Q. So, yeah.
But it could be that the reward decreased from A and C, but you see the sum of the two, so you see basically.
So this response is response evoked by A.
That's only A.
Yeah. So that also did not. Okay, so yeah.
So what's the anticipation responses when there's no Q? What's the baseline?
Yeah, that's right. Yeah, so it seems that from the behavior, there is some slight increase in the baseline. So they seem to be leaking spontaneously without Q. So that's what happens during degradation. And yeah. And that doesn't happen for the Q reward condition. Yeah.
So why there's still an increase of the anticipated relief in the previous section for the degradation?
Yeah, so this is session 5.
still increase of dose.
Yeah.
Yeah.
So this is during training. And then we just continue to condition what they do. Yeah. Maybe I should go relatively quickly, but well, I guess I kind of conveyed the main message perhaps, but so this kind of phenomenon cannot be explained by conventional TD learning model with complete serial compound. I mean, the reason is obvious, right? So what happened outside the trial is important. But this representation is locked to the Q and does not take into account the ITI. So there are a couple of ways to model this, and one is having this kind of contextual state, which lasts regardless of what happens in the task. So representing the situation in the task, continuous state. Another is very similar to the previous approach. We could construct some state model, belief state model, based on the task structure. And once you do that, then obviously it's taking into account ITI and so on and so forth. You could get this kind of V-shaped representation. Yeah. So these are predicted order A response. Now, the reason for that is during degradation, you tend to associate reward to the ITI state. Right? So this background state acquires some value because reward is delivered during that state. So the value goes up. So the TD error, which is the difference from between consecutive time point, is decreased. It's not that value is decreased, but value stays the same. But pre-Q, the value before the Q is increased because of the association. So this explains the contingency degradation. So the point that Anka paper made is this contingency degradation cannot be explained by conventional TD errors, but having proper state representations, we can start explaining these. But then these state representations are handcrafted, so we just gave the state representation by constructing, and some people might think that this is cheating, and we could create whatever. So we try to come up with better ways, unbiased way to do this, and one way to do this is recurrent neural network. So recurrent neural network received olfactory cues and reward, and then compute value based on the weighted sum of activity. And then once you get the value, you can compute TD error. And then the weight within the recurrent neural network was adjusted to minimize TD error using backpropagation. Okay. So with that, we can get a reasonable response in the network. So these are the TD error computed by value RNN. This resembles the dopamine signals that we record. So, and also we can explain contingency degradation and the effect of Q reward response, very similar to the reward, even better than handcrafted model. Okay, so the point of this is you don't really need to handcraft the states. If you can do this kind of minimization, optimization, the state representation emerges just through observation. Okay. Right. And what's happening is just briefly, we create some attractor states corresponding to the different task states. So baseline is ITI state, and that's a very stable state. And then order Q kicks out the activity and then create these dynamics. And that could correspond to the different states within the model. Right? So handcrafted model has some different states, and that could be seen as the trajectory or different states in these attractor dynamics. And we have also done that for the earlier studies. So task 1 and task 2, using value RNN, we can create these responses. And in task 2, task 1, ITI and ISI tend to be a stable fixed point or stable states. Not necessarily fixed point, but ISI tend to be stable. But in task 2, ISI is much leakier. And so these RNN trained in task 1 and task 2 create different dynamics. And this might explain value state, like state representation. Okay, so this RNN-based approach had also a great impact in the field. In this case, the study done by Jane Wan and Matt Kotubini, they trained recurrent neural network in this example, the task that I explained. So this monkey, Bromberg-Martin's monkey, performing saccade-based reversal learning task. And just by training in this task, it seems that the network can learn the anti-correlation between left target and right target, and as a result, you can see this inference-based response in the network. So the recurrent neural network, so this kind of representations created in recurrent neural network or dynamics of it can start to explain some of these non-trivial dopamine responses. So again, so this is a kind of situation where classical TD learning model fails, but the network that is able to learn these correlational structures can start to explain these responses. So the failure of the original model does not necessarily mean the end of TD learning. Okay, so and Anchor, what Anchor does is even if you explore various parameters, it doesn't create much difference between degraded and queued reward response. So it is really insensitive to the kind of thing that we discussed. Okay. All right, so that's it. And so the main message is, so so the problem of what state representation is used is very important. And indeed, a lot of the most difficult issues in RL is dealt within the state representation. So in some sense, if you have good state representations, reinforcement learning can be very efficient, but otherwise, reinforcement learning might not work. So what kind of state representation is used, and also how to build this kind of state representation is going to be a very, very important issue in the future, and it's going to be a hot topic. Okay, so with that, I'd like to thank the people who did the work. Selina led the contingency integration work together with Matt Barrett. Matt did most of the modeling, and the RNN-based approach was done by Jay Henning, and all the project was collaboration with Sam Gershman. So thank you very much for your attention.
Thoughts or comments about, I guess, like less binarized reward outcomes? I know we did play a little bit with like, the magnitude of it, but I guess like richer types of rewards, maybe like social rewards or other cases. I'm just curious how you think about like more naturalistic reward processing.
Yeah, that's interesting. So, what is the reward, right? So you eat some cake, right? And then you taste it, and that will activate dopamine. But what the brain or body cares is not necessarily the sweet taste. And what matters is the nutrition that the body can get eventually, like 30 minutes or 1 hour later. So one way to think about this is this taste is also not the primary reward, but something that evolutionary process learned that this is a good predictor of future nutritional benefit. And then this seems to be indeed the case, such that if you use, for example, artificial sweetener, and this doesn't result in nutritional benefit, eventually animals stop pursuing that kind of food associated with artificial sweetener. So there's always a checking system that whether this kind of something that seems to predict reward is actually a good thing or not. So I think eventually it boils down to what benefit the body can get. That will define the reward. But also this is kind of embedded in the evolutionary process that work pretty well in many situations. So dissociating them could be quite difficult oftentimes. But that's a very active area of research.
Sometimes it's difficult to judge whether reward follows the cue because there could be long delay between it, and the delay could be variable. So I was just wondering, so in animals learning, they should be sensitive to this timing. And in your RNN, do you think what kind of timing innovation does it capture? And if its hyperparameter changes, will it show different responses?
Yeah. So the brain seems to use all possible cues or logics to solve the issue. This is exactly the Simon program, right? And for example, if you eat something and then get sick, you don't necessarily associate that sickness to the cue that is present around your scene. Instead, something that you ingested is very likely the cause of nausea and things like that. So it seems there's such a logic. And also another important aspect is novelty. So if you're in a familiar environment and suddenly you see something new, it's likely that something happened that didn't happen before is credited to the new stimulus. So the brain seems to have the mechanisms to boost processing of novel stimuli, and that is related to credit cyanide.
So what do you think the RNN, if you change its hyperparameter, can
RNN
do the same?
Yeah, you could use novelty as a kind of boosting of the processing. Right? So yeah, it boils down to whatever mechanism you can think of to increase the credit assignment. So novelty or some particular modality of stimuli, you try to give more credit to likely causes.
Thank you.
One last question from
Just a thought experiment. So let's assume, or kind of like a very imaginary situation. So let's assume that we have an animal in a very complex environment, and the animal has a perfect model of the world. So everything is predictable. So according to this theory, you won't have, according to standard TV, you won't have any error prediction signals. By definition, in this imaginary situation. I know that this
So there's some, yeah, okay, you continue.
And yeah, I guess that you're going to argue, yeah, but we see these value signals anyway. But in the standard TV, there are no error signals. So there is, this would contradict the, so essentially you won't have any dopamine release in the string case of all this theory. So it's kind of weird. No? So this is not possible as a good model of behavior. So you should have other kind of signals that tell you, well, this is something that you have to choose right now, anyways. So how do you see this imaginary process experiment? Whether this challenges the general concept of RL, whether this challenges the general concept of error prediction signals, reward prediction signals in the brain, or is like something that you will never encounter this paradox.
So even in steady, even in the deterministic case, reaching to the steady state, optimal value function, this algorithm could still be useful. But I would argue that in the world, it's almost impossible to eliminate all the stochasticity. or unpredictability.
Yeah,
Right.
but, yeah.
So-
So thinking about, we are theorists,
Yeah.
theorists, so we like thinking about the, like really very, so what would be your prediction? What will happen in that case? Yeah, I know that the value function will be learned, the policy will be learned, but then there won't be any dopamine release
So stochasticity,
in this system, or?
stochasticity, let's think about some stimulus predicted value is 0.5 seconds. And even if you know the probability exactly 0.5, and that's your precise knowledge of the world, there's also stochasticity remain in that situation, right? So where reward could be positive or negative, reward may or may not come. So during that time, you will get positive or negative prediction.
Yeah, but let's assume that you have a perfect model and you know that this is stochastic.
Yeah.
So do you have, in that case, error prediction signal if you know that it's stochastic and there is nothing else that you can learn?
Well, yeah, I guess as long as there's prediction error signals, whether it's useful or not, it's causing the value estimate to go up and down. So there's always some update process, unless you stop it. So
yeah, that's the point, that you know perfectly well the value function.
yeah. Well, I guess maybe we can continue this during VR or something.